Hello and welcome back at the FinetLink channel where we are studying about the routing concepts and we are in the part 2. In the part 1 we explained how routers determine the best path. We explained how routers forwarded packets to the destination and then we reminded some basic configuration setting on a router. And what we will do now is we will describe the structure of a routing table and then we will compare static and dynamic routing concepts. How does a router know where it sends the packet? That's the question. We know that a router creates a routing table that is based on the network when it is located. And remember that we said that the routing table contains a list of routes not to a known network, and the source for this information is derived from the directly connected network by the static routes and the dynamic routes, which are learned by the dynamic routing protocol. Here in this figure, we have router 1 and router 2 that are configured, and they are using the dynamic routing protocol open short path first to share routing information. And in addition, we have the router 2 that is configured with a default static route to internet service provider. And if we use the show IP route command for both of those routers, we will be able to see the routing table of each of them. And in this routing table, we are able to see that we have some source for each route, and they are identified by a code. The code identifies how the route was learned. So we have, as you can see, we have the add code, which identifies the address assigned to a router interface, and this allows the router to effectively determine when it receives a packet for the interface instead of being forwarded. We have the code C, which identifies the directly connected network. For example, if we are the router 1, we can see that we are directly connected by the code C with the 10.0.1.0/24 network through the Giga Ethernet 0/0/0, and we can reach this network through the interface Giga Ethernet 0/0/0 with the IP 10.0.1.1/32. And also we have the code O that identifies a dynamically learned network from another router, and in this case we are using the open short path first routing protocol, which means that we are able to learn about the network 10.0.4.0/24 and 10.0.5.0/24 by using the open short path first routing protocol. And we have the information through which serial interface we will be able to locate this network and from which IP, which the via 10.0.3.2 tells the next hop, which in this case is the router 2. And we have also the star, where the star identifies the candidate route for a default route. And we have the S, which identifies a static route created to reach a specific network. And both of them you can see that are located here. The default route is the first route that is listed in the routing table. And there are 3 routing table principles that are described here in this table. And there are issues that are addressed by the proper configuration of a dynamic routing protocol or static routes on all the routers between the source and the destination device. So here are listed the principles and there are explanations. And here in this case are referring to the network that we had listed in the slide before. So if every router makes its destination alone based on the information it has in its own routing table, and in this case router 1 can only forward packets using its own routing table, and router 1 does not know what routes are in the routing table of the other router. For example, in our example, we have router 2. The information in a routing table of one of the routers does not necessarily match to the routing table of another router. And in here, just because router 1 has a route in its routing table to a network in the internet via router 2, that does not mean that the router 2 knows about the same network. Probably he has other network listed in his routing table. Routing information about a path does not provide return routing information, which means, the example for our network, router 1 receives a packet with the destination IP address of PC1 and the source IP address of PC3. Just because router 1 knows to forward the packet to its Giga Ethernet 0/0/0 interface doesn't necessarily mean that it knows how to forward packets originating from PC1 back to remote network of the PC3. And as a network administrator, it is imperative to know how to interpret the content of IPv4 and the IPv6 routing table. And here in this table is displayed the IPv4 and IPv6 routing table entries on the router 1 for the route to the remote network 10.0.4.0/24 and the network that is listed on the IPv6, which is 2001 DB8 ACAD 4/26. And by those routing table entries, what we are able to identify is the route source, which tell us how the route was learned, and here in this case is learned by Open Short Path First protocol, which means it's dynamically learned by the routing protocols. And we have the destination network address, which shows the network ID for the route, followed by the subnet mask. And then we have the administrative distance is a measure route trustworthiness used to break ties between different sources, and the metric, it's a cost value, which indicates how good this route is. And then is the next hop, which is the IP address of the next router in the path to the destination, the time when it was learned at the routing table, and every time it makes updates. And then we have the outgoing interface, which is the physical port on the router where the packet leaves. Same is even for the IPv6. We have the route source, we have the destination network address followed by the subnet mask, the administrative distance and the metric. We have the next hop and the outgoing interface. And remember this, before a router can learn about any remote network, it must have at least one active interface configured with an IP address and subnet mask. And this is known as a directly connected network or directly connected route. Routers add a directly connected route to its routing table when an interface is configured with an IP address and is activated. A directly connected network is denoted by a status code of C, as we mentioned in the routing table, and the route contains a network prefix and the prefix length. The route table also contains a local route for each of its directly connected networks, which is indicated by the status code of L. And this is the IP address that is assigned to the interface on that directly connected network. And for IPv4 local routers, the prefix length is /32 for the local routes, and the IPv6 local route, the prefix length is 128. And this means that the destination IP address of the packets must match all the bits in the local route for this route to be a match. The purpose of the local route is to effectively determine when it receives a packet for the interface instead of packets that needs to be forwarded. Directly connected network and local routes you will be able to see even in this show IP route for the router 1 for both networks, for IPv4 and IPv6. And as you can see, we are able to see the directly connected networks and local route as is indicated by the route code. After directly connected interfaces are configured and added to the routing table, static or dynamic routing can be implemented for assigning remote networks. Static routes are manually configured. They define an explicit path between two networking devices. Unlike a dynamic routing protocol, static routes are uses that are not automatically updated and must be manually reconfigured if the network topology changes. The benefit of using those static routes include improvement security and resource efficiency. Static routes use less bandwidth than dynamic routing protocols, and no CPU cycles are used to calculate and communicate routes. The main disadvantage to using static route is the lack of automatic reconfiguration if the network topology changes. So there are three primary uses for the static route, as you can see, that are listed here in this slide. It provides easy of routing table maintained in smaller networks that are not expected to grow significantly, and it uses a single default route to represent the path to any network that does not have a more specific match with another route in the routing table, and the default routes are used to send traffic to any destination beyond the next upstream router. If a router to and from the subnetwork, where the subnetwork is a network accessed by a single route and the router has only one neighbor. Here we will have a figure that shows an example of a stub network. You can see that any network attached to router 1 would only have one way to reach other destination, whether to network attached to router 2 or to destination beyond router 2. This means that the networks 10.0.1/24 and 10.0.2.0/24 are stub networks, and router 1 is a stub router. Here, in this example, we can see that a static route can be configured on router 2 to reach the router 1 networks. Additionally, because router 1 has only one way to send out non-local traffic, a default static route can be configured on router 1 to point to router 2 as the next hop for all of the networks. So, for demonstrating static routes, the topology here and in this figure is simplified to show only one LAN attached to each router. Here, the figures show IPv4 and IPv6 static routes configured on router 1 to reach networks on router 2 for both IPv4 and IPv6. We are not explaining the configuration commands because we will explain them in a later topics, but here we will have an output that shows that IPv4 and IPv6 static route entries on router 1 that can reach the IPv4 and IPv6 networks on router 2. We can see that both entries use the status code as S, which indicate that this route was learned by a static route. Both entries also include the IP address for the next hop router via the IP address. and the static parameter at the end of the command display only static routes. And as for the dynamic routes, we can say that the dynamic routing protocol are used by routers to automatically share information about the reachability and status of remote networks. Dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. Important advantage of dynamic routing protocols are the ability to select the best path and the ability to automatically discover a new best path when there is a change in the topology. Network discovery is the ability of a routing protocol to share information about the network that is known about with other routers, and they're also using the same routing protocol. Instead of depending on manually configured static routes to the remote networks on every router, a dynamic routing protocol allows the router to automatically learn about these networks from other routers. These networks and the best path to each are added to the routing table of the router and identified as networks learned by a specific dynamic routing protocol. And here we have shown router 1 and router 2 that are using common routing protocol to share network information between each other. And as a previous example used for the static route, how we can reach the IPv4 and IPv6 networks on the router 2, the static routes are no longer configured, and the open short path first is now added, used to dynamically learn all the networks connected to router 1 and router 2. Here in the following examples, we can see that the IPv4 and IPv6 open short path first routing entries on router 1 can reach this network on the router 2. We can see here that both routing entries now don't use an S code, but they use an O code to indicate that the route was learned by the open short path first routing protocol. Both entries also include the IP address of the next hop router via the IP address. And remember that we mentioned even a default route, where a default route is similar to a default gateway on a host. The default route specifies a next hop router to use when a routing table does not contain a specific route that matches the destination IP address. A default route can be either a static route or learned automatically from a dynamic routing protocol. A default route has an IPv4 route entry as all the octets would be 0 with a subnet mask 0, and an IPv6 route with all the hextet 0/0 as a subnet prefix length. This means that the 0 or no bits needs to match between the destination IP addresses and the default route. Most enterprise routers have a default route in their routing table. This is to reduce the number of routes in a routing table. A router such as a home or small office router that only has one LAN may reach all its remote network through a default route, and this is useful when the router has only directly connected networks that one exit point to a service provider router. Here in this figure, router 1 and router 2 are using open short path first to share routing information about their own networks, and router 2 has a static default route to its Internet Service Provider router. Router 2 will forward any packets with a destination IP address that does not specifically match on one of the networks in his routing table to the Internet Service Provider router. This will include all packets designated to the Internet. And as you can see, router 2 has shared its default route with router 1 using open short path first. Router 1 will now have a default route to its routing table that is learned dynamically from open short path first. Router 1 will also forward packets with a destination IP address that does not specifically match one of the networks in its routing table to router 1. And here in this example, we show IPv4 and IPv6 routing table entries for the static default routes configured on router 2. Let's analyze the structure of an IPv4 routing table. An IPv4 was standardized in the early 1980s using the now obsolete classful addressing architecture. For the IPv4 routing table is organized using the same classful structure. Here in the show IP route output, we can see that some route entries are left justified while others are intended. This is based on how the routing process searched the IPv4 routing table for the longest match. This was all because of classful addressing. Although the lookup process no longer uses classes, the structure of the IPv4 routing table still remains in this format. Although the table of the structure are beyond scope of this module, it is helpful to recognize the structure of the table. An intended entry is known as a child route. A route entry is intended if it is the subnet of a classful address, class A, B, or C network. Directly connected network will always be intended child route because the local address of the interface is always entered in the routing table as a /32. The child route will include the route source and all the information such as NAT hop address. The classful network address of this subnet will be shown above the route entry less intended and without a source code. The route is known as a parent route. Here in the second show IP route, there is an example that shows IPv4 routing table on the router 1 for the topology of the network that we had before. We can see that all the network in the topology are subnets, which are child routes of the class A network and with the parent route as 10.0.0.0/8. And there are 8 subnets. With 2 different subnet masks, 4 for each, which is directly connected, and the local 4 directly connected and 4 local routes. The concept of classful addressing was never part of the IPv6 routing table and is straightforward. Every IPv6 route entry is formatted and aligned the same way compared to the IPv4 that had parent route and child route. A route entry for a specific network address, which is prefix and prefix length, can only appear once in the routing table. However, it is possible that the routing table learns about the same network address from more than one routing source. Except for the very specific circumstance, only one dynamic routing protocol should be implemented on a router. However, it is possible to configure both open short path first and enhanced interior gateway routing protocol on a router, and both routing protocols may learn the same destination network. Each routing protocol may decide on a different path to reach the destination based on the metric on that routing protocol, which raises a few questions. How does the router know which source be used and which route should it install in the routing table? Because the route learns from the open short path first, or the route learned from the Exchange Interior Gateway Routing Protocol. Cisco IOS use what is known as administrative distance to determine the route to install in its routing table. The administrative distance represents the truthiness of the route. The lower the AD, the more trustworthy the route source. Because those two protocols has different administrative distance, the route entry will be installed at the routing table, the route entry of the protocol with the lowest administrative distance. A more common example is a router learning the same network address from a static route and a dynamic routing protocol, such as Open Short Path First. A static route has an administrative distance of 1. Whenever the Open Short Path First, the administrative distance is 110. Given to separate route source to the same destination, the route chooses to install the route with the lowest administrative distance. And when a route has a choice of static route and an open short path first route, the static route takes the precedence, which means that route will be listed in the routing table. And remember that directly connected network have the lowest administrative distance as 0. Only a directed network can have the administrative as 0. Here in this table, there is a list of various routing protocols and their associated administrative distance. But since we have static routes and dynamic routes, the point is which one we have to use. And since we discussed the way that a router creates its routing table, and now that we know about the routing, like IP addressing can be either static or dynamic, the question is, should we use static or dynamic routing? The answer is both, because static and dynamic routing are not mutually exclusive. Rather, most networks use a combination of dynamic routing protocol and static routes, because static routes are commonly used in the scenarios where, as a default route, forwarding package to a service provider, or for routes outside the network domain and not learned by the dynamic routing protocol, or when the network administrators want to explicitly define the path of a specific network, and for routing between stop networks. Static routes are useful for smaller networks with only one path to an outside network. They also provide security in a larger network for certain types of traffic or links to other networks that needs more control. And as for the dynamic routing protocols, which mean dynamic routes, they have the network administrator manage the time-consuming and extracting process of configuration and maintaining static routes. Dynamic routing protocols are implemented in any type of network consisting of more than just a few routers. Dynamic routing protocols are scalable and automatically determine better routes if there is a change in the topology, which means that they are more commonly used in the networks of more than just a few routers. When change in the network topology requires the network to automatically determine another path, or for scalability, as the network grows, the dynamic routing protocol automatically learns about new network. Here in this table, we have a comparison of some differences between dynamic and static routing. Dynamic routing protocols have been used in networks since the late 1980s. One of the first routing protocols was the Routing Information Protocol, and then came the vision. As network evolved and became more complex, new routing protocol emerged. The Routing Information Protocol was updated to the version 2 to accommodate growth in the network environment. However, the version 2 still does not scale the larger network implementation of today. To address the need of larger network, two advanced routing protocols were developed: Open Short Path first and Intermediate System to Intermediate System. And then Cisco developed the Interior Gateway Routing Protocol, which was later replaced by Enhanced Interior Gateway Routing Protocol, which also scales well in larger implementation. Additionally, there was the need to connect the different routing domains or different organizations and provide routing between them. So the Border Gateway Protocol, as the successor of Exterior Gateway Protocol, is used between Internet service providers. And the Border Gateway Protocol is also used between Internet service provider and some private organization to exchange routing information. And here in this figure, we display the timeline of various protocols and where were these protocols introduced to the network. And to support the IPv6 communication, newer versions of the IP routing protocols have been developed, as it is shown here in this IPv6 row in the table. The table classifies the current routing protocol, Interior Gateway Protocol, as a routing protocol used to exchange routing information with a routing domain administered by a single organization. This is only one Exterior Gateway Protocol, and it is Border Gateway Protocol. Border Gateway is used to exchange routing information between different organizations known as autonomous systems. And Border Gateway Protocol is used by Internet service providers to route packets to the Internet. Distance vector, link states, and path vector routing protocols refer to the type of routing algorithm used to determine the best path. And a routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the choice of the best path. The purpose of the dynamic routing protocol includes the following: discovery of remote network, maintaining up-to-date routing information, choosing the best path to destination network, and ability to find a new best path if the current path is no longer available. And the main components of a dynamic routing protocol will include the data structure, which is a routing protocol typically used table or database for their operation, and this information is kept in random access memory. And we have the routing protocol messages, where the routing protocol uses various types of messages to discover neighbors, routers, exchange route information, and other tasks to learn and maintain accurate information about the network. And as for algorithm, it is a finite list of steps used to accomplish a task, where the routing protocol uses algorithm for facilitating routing information and for the best path of determination. Routing protocol will allow a router to dynamically share information about remote networks and automatically offers this information to their own routing table. And here you can see the process, how they update and the information and share the information with each other. Routing protocol determines the best path or route to each network and that route is then offered to the routing table. The route will be installed in the routing table if there is no other routing source with a lower administrative distance. A primary benefit of the dynamic routing protocol is that the routers exchange route information when there is a topology change. This exchange allows routers to automatically learn about new networks and find alternative paths when there is a link failure to a current network. Before a path to a remote network is offered to the routing table, the dynamic routing protocol must determine the best path to that network. Determining the best path may involve the evaluation of multiple paths to the same destination network and selecting the optimum or shortest path to reach the destination. Whenever multiple paths to the same network exist, each path uses a different exit interface on the router to reach that network. The best path is selected by a routing protocol based on the value or metric used to determine the distance to reach a network. A metric is the quantitative value used to measure the distance to a given network. The best path to a network is the path with the lowest metric. Dynamic routing protocols typically use their own rules and metrics to build and update routing tables. The routing algorithm generates a value or a metric for each path through the network. Metrics can be used on either a single characteristic or several characteristics of a path. Some routing protocols can base route selecting on multiple metrics, combining them into a single one. Here in this table, we have a list of some common dynamic protocols and their metrics that they use for reaching other networks. And we also have an animation which highlights how the path may be different depending on the metric being used. If the best path fails, the dynamic routing protocol will automatically select a new best path if one exists. But what happens if a routing table has two or more paths with identical metric to the same network? Because when a router has two or more paths to a destination with equal cost matrix, the router can forward the packets using both paths equally. This is called equal cost load balancing. The routing table contains a single destination network but has multiple exit interfaces, one for each equal cost path. The router forwards packets using the multiple exit interface listed in the routing table. If configured correctly, load balancing can increase the effectiveness and performance of the network. Equal cost load balancing is implemented automatically by dynamic routing protocol, and it is enabled with static routes when there are multiple static routes to the same destination network using different next hop router. And here we have an example that provides the equal cost load balancing. And with this, we are ending all the information about routing concept. And thank you for being with us. Do not forget to subscribe to this channel if you are new to it. And if you like the video, share it with your friend. It will help us grow as a channel. Thank you.